to test the ultrasonics on the ABS. This is the last line of defence, designed for doors with no pillars around the windows, or vans with big windows that pop out without breaking anything.
Ultrasonic sensors work by triggering the alarm if a change in air pressure or movement is detected. This makes them a very effective upgrade to protect the cabin of the car.
So it basically picks up any movement inside the car, which will set the alarm off.
Alright, what's up, y'all? We're going to talk about our first example of ultrasonic sensors and how they relate to speed, distance, and time. So I'm going to first start off with distance, speed, and time. Alright, and the way that these three equations work is that if I have a very fast speed, essentially I'm probably going to have a short time. If I have a very fast speed, I'm going to cover a large distance. Okay? And usually if I have a very big distance multiplied by a time, I'll have a big speed. Alright, so we said that ultrasonic sensors work by emitting sound waves through air, and it hits some type of object, bounces off the object, and goes back to the receiving part of the sensor. And we said that sound waves travel at 340 meters per second. And we said that this is very, very fast. Okay? Because this is very, very fast, our speed of the time that it takes for our sound wave to bounce back is going to be on the scale of a microscale. It's going to be very, very small. All right, very, very short. And let's say the distance of the person inside the car was 10 centimeters. 10 centimeters is essentially, it's your pinky finger. It's like the very top part of your pinky finger. It's about 10 of those. So it's a very short distance, which makes sense, right? Because he was inside of the car, and the car was so enclosed, right? So before we solve for the time, how long does it take for the alarm to go off, right? That's what we want to know. We want to know how long does it take for the alarm to go off. That's essentially how long does it take for the sound wave to hit the person, the object, and bounce back to the receiver and then do some type of action. All right. So before we solve for that, we have to first put our speed in terms of centimeters and microseconds. And that's just the rule when you're doing physics. You always have to put all the units in the same unit, right? They have to match up so they can cancel out and you can get the correct answer. If you don't do that, your answer will be wrong. All right. So let's first start off with converting. So this is going to be a two-step conversion, 2 T-charts. All right, and we need our conversion factors from centimeters to meters and from microseconds to seconds. So we know that there is 1 meter. There's going to be 100 centimeters in that 1 meter. And for 1 microsecond, that's going to be 0.0000001 seconds. Okay? Let me make sure that's right. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so that's how small a microsecond is. So it's a very short time. All right, and what we're going to do, we're going to match the units diagonally. All right, so let me show you what I mean by that. So let's first start off with this top conversion. It doesn't matter which one you start off with as long as they match diagonally. So I have a meter at the top of here, so I want to put 1 meter here. And how many centimeters are in 1 meter? 100 centimeters. So that's going to go at the top. All right, and you know you did it right because the units will cross out diagonally. And that's all you're doing. You're just crossing out the units diagonally. So we have a second at the bottom here, and we have a second over here. So we're going to put that at the top because that will cross out diagonally. 1, 2, 3, 4, 5. Seconds. And then how many microseconds? That's 1 microsecond. All right. So, you know you did it correctly because the seconds will cross out. Okay. Now, once you have your units in terms of centimeters and microseconds, have a centimeter here and have a microsecond here, they're not crossed out because that's what we want. All you do is just multiply the top and multiply the bottom. All right. I didn't tell you all here, but there's always a 1 under here because that's a reciprocal of 1. So 1 over 340 would be 3 over 340 over 1. And so there's always a 1 here, but you don't have to put it there because ones are, you know, you can put them in. Sometimes you don't have to put them. All right. And so it's just going to be 340 times 100 times 0.00001 second over 1 times 1 times 1. Okay. And our new speed is going to be, 0.0344 centimeters per microsecond. Okay, so this is our new speed. All right, it's in terms of centimeters and microseconds. All right, so now all we have to do is just solve for time. All right, so we know that the equation for time, this is your imaginary triangle. This is a tool that is used to figure out the equations for speed, distance, and time. All right, so you have x at the top, speed at the bottom, time right here. All right, so if we cover up the t, the equation is going to be x over s. So time is distance, which is x, over s, which is speed. All right, so now all we're going to do is just substitute our distance and our speed to figure out how long it takes for the alarm clock to go off, the alarm clock to go off, the alarm to go off. All right, so the distance is going to be 10, right? We're just doing a substitution, divided by the speed, which is 0.0344 centimeters per microsecond. All right, so 10 divided by 0.0344 microseconds is 290. So now we have to divide our units up. So we have a whole centimeter at the top, and we have a centimeter divided by a microsecond. All right, so this is you're dividing fractions pretty much. That's what this is. So you use the keep, change, flip method. So you're going to keep centimeters the same. You're going to change this division to multiplication, and you're going to flip that fraction. And it's going to be microsecond over centimeter. All right. And as you can see, like over here, we say there's a property when you have the same units diagonally, they cross out. So same thing here. The units will cross out diagonally. And so you're left with a microsecond. So the answer is 290 microseconds. All right, and so for people who don't understand what that means, so that is 0.000290 seconds. So that is 1, 2, 3, 4, 5, 6 times smaller than 1 second. All right, so that's very, very, very fast. Very, very short. Very, very short.